it is now time to build properties, more tools that will allow us to show that functions are continuous at a point or in an interval in an easier way. Again, we can't always rely on graphs. So we have to be able to find algebraic mechanisms for showing that functions are continuous. We already know that constant functions are continuous everywhere in their domain. Let's write that down. So constant functions. For example, if f of x happens to be equal to c, then we already know that the limit as x approaches a of f of x is equal to the limit as x approaches a of c, which is equal to c. And c, you know, is equal to f of a. So when we put the very first expression and the last expression together, that shows continuity. And I want to emphasize that this is true for all real numbers x. So constant functions are continuous on all of the real numbers, and all real numbers is the domain of a constant function. Another function, the simple linear function. Okay. So in other words, f of x equals to x. We already know here that the limit as x approaches a of f of x, which is equal to the limit as x approaches a of x, this is going to be equal to a, and a is f of a. So again, this happens for all x in R. As a result, then we also have power functions. Power functions. Here we are going to be assuming that n is natural, a natural number. So we know that n is positive. So in this case, we know that if f of x is equal to x to the n, then again, that means that the limit as x approaches a of f of x is going to be equal to the limit as x approaches a of x to the n. And then that is going to be equal to a to the n. And a to the n is f of a. And this is true again for all real numbers, for any real number. Similarly, we're going to have, let's say, rational power functions. Let's call them like this. These are functions of the form f of x equals x to the p over q. Again, assuming here that p over q is in lowest terms. So if we now take the limit as x approaches a of f of x, and a must be in the domain of this function, then we are going to have that this is equal to the limit as x approaches a of x to the p over q. By properties of limits in section 2.3, this is the same thing, if you remember, as applying the limit to the inner function right here, which is just x, and the limit as x goes to a of x is a. So this just becomes a to the p over q. And I just want to make sure again that we go back to this agreement that if the denominator of the exponent is even, a has to be positive. Because if it's even, imagine that q is like 2, then that transfer to taking a square root, and the square root of a negative number is undefined. So we are conforming to all of those conditions here, that if q is even, a has to be positive. That if p over q is negative, In which case, for example, if it's negative, imagine that we had a to the negative 3 over 2, something like that. Then this is equivalent to having 1 over a to the 3 over 2. So in this case, we have to make sure then that a is non-zero, because if a is 0, the entire number is undefined. So we are still keeping all of those agreements here, that this number a to the p over q has to make sense. But my goodness, this is quite elaborate already. Let me put over here that this is true for all x in the domain of the function f of x. So we already know, if we start looking at our list over here, that constant functions are continuous for every x within the real numbers. Linear functions, same thing, continuous at every x within the real numbers. Power functions, where n is a natural number, continuous for every x in the real numbers. And power functions of the form x to the p over q are continuous everywhere in their domain. So nice. Now, these are not the only tools that we need. We need more. Now we need tools that will talk about operations, adding continuous functions, multiplying continuous functions, and so forth. So we're going to go ahead now and do that as well. Let's start now thinking about what happens if we add continuous functions. What happens if we multiply continuous functions at a point A? How do we handle situations like that? Okay. So let's first develop what is known as basic laws of continuity. After we develop those laws, we're going to briefly talk about continuity of polynomials and rational functions. So starting here with this initial condition, suppose that f and g are continuous functions at x equals a. That's very, very important. We are starting with a function f of x that is continuous at a. In other words, we know that the limit as x approaches a of f of x is going to be equal to f of a. So this is something that we know. We also know that g is continuous. So the limit as x approaches a of g of x is going to be equal to g of a. So we are starting with two continuous functions at a point x equals a. So if this is the case, we're going to say then, let me use different color, then the following functions are also continuous at x equals a. So what functions are those? Number one, if we decide to consider a function which consists of the sum of f of x plus g of x, or let's say f of x minus g of x, then in this case, the sum or the difference will also be continuous. And this will be continuous because f is continuous and g is continuous at x equals a. So the sum is also going to be continuous. The difference will also be continuous. I want you to realize that just as with properties of limits, when it comes to the sum, we are not restricted to the sum of two functions. We can add as many continuous functions as we want. F of x plus g of x plus h of x plus k of x, and you can continue building functions through addition. The point is, if you add functions that are continuous at a, then the sum of all of those functions will be another continuous function at a. Now, going on to property number 2, this will involve multiplication. This will say that if we create a new function, which is the product of f and g, then the product function is also continuous at x equals a. And when talking about multiplication, once again, we are not limited to multiplying two functions. I can multiply as many continuous functions as I wish, and the product of all of those functions will also be continuous at x equals a. And then property number 3 will say, well, what happens if we build a new function which consists of a numerical coefficient times one of these continuous functions, let's say f of x, or let's say c times g of x. The point is that if I take a continuous function and I multiply by any number, a simple number that doesn't involve a variable, that's why it's a numerical coefficient, something like 3, like 4, like minus pi, then the new function that I obtain will continue being continuous at x equals a. Similarly, c times g of x will remain continuous. And then we need division. So that's property number 4. Division will say that if we build a new function, which is equal to f of x over g of x, then this new function right here will be continuous as long as g of a does not equal to 0, right? Because whenever we talk about continuity, we're going to go ahead and take the limit as x approaches a of f of x over g of x. And we want to make sure that at a, if we want to end up with f of a over g of a, this is the condition for continuity, we want to make sure that g of a, since it appears in the denominator, is non-zero. Otherwise, division is going to be undefined. So in addition to the previous 4 or 5 functions that we just discussed, now we have 4 additional properties that will help us manipulate functions that consist of sums, multiplication, and division. So these properties should also go in our toolbox for arguing for continuity of functions. Let's talk about polynomials now. A quadratic is a polynomial. A simple, beautiful parabola is, by definition, a polynomial. The cubic function, y equals x cubed, is a polynomial. And just by adding power terms, just by adding x to the n, you end up building very massive polynomials. So, for example, something of the form p of x equals 3x to the 7th minus 2x to the 6th plus 1/2 x to the 5th minus 3x to the 4th. I'm going to skip a term to go faster, plus 2x squared minus pi. This over here is a beautiful, beautiful polynomial. And what this theorem, the first part of this theorem is going to tell us is that all polynomials are continuous everywhere in their domain. And if you recall, the domain of any polynomial consists of all real numbers. Every single real number is in the domain of a polynomial. If you look at this polynomial here on the right, it makes sense for us to be continuous because a polynomial consists of adding and subtracting power terms. And we already established in this video, even in the previous videos, that power functions, these terms individually, if you think of each of these terms as a mini function right here, these are all power functions. And power functions involving a constant like pi, power functions are continuous. So by the properties that we just developed, when we add continuous functions, we get another continuous function. So if 3x to the 7th, negative 2x to the 6th, 1/2 x to the 5th, if all of these individual power functions are continuous, the sum and the difference, so this new function will be continuous as well. So the continuity of polynomials is pretty straightforward. Just want to make a mention here that whenever I write THM, this is just a shortcut for theorem, right? Then theorems are fundamental, proven results in mathematics. So the theorem begins like this. It begins with two polynomials, P of x and Q of x, and this can be any two polynomials. And it says that the first part of the theorem will say that if P and Q are indeed polynomials, then number one, P of x and Q of x are continuous. They are continuous for all x within the real numbers. We needed something like this because we are building tools, we are collecting tools, and this is another tool that we can put in our toolbox. Now we know that every time that we see a polynomial, that polynomial is automatically continuous at every x in its domain, and the domain of a polynomial is infinite. Now, number two, rational functions. If you remember, rational functions are built by creating a quotient of a polynomial over a polynomial. So whenever you have a polynomial divided by a polynomial, you have created a rational function. So this theorem will say that rational functions are continuous. So this is continuous for all x in the domain. We're going to say in the domain of P of x over Q of x. In other words, we have to make sure whenever we say for all x in the domain, we are really saying here that Q of x shouldn't be equal to 0, because if Q of x is equal to 0, then we have an undefined expression. So this is the only slight modification, but I know that by now you are used to that whenever we have division, whenever we have a denominator, anything that makes your denominator equal to 0 has to be excluded. If we look at example 1 right here, they're asking us, where is the following function continuous? When you look at the function, you notice that this is a rational function. This is a polynomial, a third-degree polynomial over another linear polynomial. A polynomial over a polynomial, by definition, is a rational function. By the previous theorem, we already know that a rational function is continuous for every x in the domain of the function. So what I have to determine here is what is the domain of this function. So practically then, the domain of f consists of every real number except when the denominator is 0. So I have to make sure that I have to make sure to find out when is the denominator equal to 0. And this is going to be equal to 0 when 5 is equal to 3x. In other words, when x is equal to 5 divided by 3. That means that the domain of this function, d, pretty much consists of all x values such that x is not equal to 5 over 3, where x can be any other real number. I am hoping that you recognize this as set notation. Practically, we are saying here, it's just a very formal way of saying that x cannot be equal to 5 over 3. Any other x value is fine except this one right here. And then this is just saying that x is a real number. We are only dealing with real numbers, not with complex numbers or anything like that. So now that we found that domain, we will say that f is continuous pretty much for all of the x values that I just stated. X is continuous here. But I'm going to say here to make it a little bit more, to make it a little bit clearer, that f is continuous for all real numbers x such that x does not equal to 5/3. Okay. So x will be continuous for every real number x except when x is equal to 5/3. So in other words, what we are saying is that f is going to be continuous in the same interval as the domain of the function. It is going to be continuous for all x values except for 5/3. And again, a reminder that that all of the other x values are real numbers. Just briefly here, prior to calculus, you've had so many pre-calculus classes, so many teachers, and everybody's different. There are always differences in how we express intervals, how we express sets. I know that in earlier pre-calculus classes, we tend to focus on set notation, and then a little bit later on, we bring interval notation. So just to go over some of that to make sure that now here in calculus, we all understand each other in the same way. Whenever we specify set notation has three components here. This part, which introduces the variable. In other words, are we going to be working with x or y or z or v? This condition here introduces conditions or restrictions. If you're going to say x has to be between 0 and 1, that goes here. Or if you're excluding a value, as we are right here, we are excluding 5/3, that goes here. And then this, the very last part over here reminds us about the set where we are working on. Are we working within the natural numbers? Is x an integer only, or is x any real number? So that usually goes over here at the end. And this bar right here, verbally, is pronounced as such that. So that's when you're going to hear me always say the set of all x such that, then the condition or restriction, and then where x lives. X is a member, x is a number, or an element of the real numbers. If x belongs only in the natural numbers, so we will say over here x is in n, for example. But because it's real number, we use that notation for the real numbers. In interval notation, you would write this. So practically what you have in interval notation, you have 5/3 and you are excluding 5/3. But you are including everything from -infinity to 5/3 and from 5/3 to +infinity, except 5/3. So in interval notation, this will be from -infinity to 5/3, not including 5/3, and then from 5/3, not including it, to +infinity. And then in the middle, to join the two, we use the union symbol. This union symbol means or. It's kind of binding, I should say, that two together. So this is saying x can be here or x can be here, but x cannot be 5/3. And we know that because we have soft brackets around 5/3. So anything on the left of 5/3 or anything on the right of 5/3, but not 5/3. So interval notation, set notation, and we're going to use them both interchangeably. Now let's talk about continuity of inverse functions. We're going to start by saying that suppose that f is a function and f has an inverse function, because not all functions are invertible. So we are taking a function f that happens to be invertible, and that inverse is going to be a beautiful function as well. So here we are going to imagine, just to give you a refresher about continuous functions, let's say that this blob right here is the domain of our function f. Let's call the domain D, and this other blob right here, it's the range. Let's call it R. So f takes everything in D and gives you everything in R. So here, the domain and the range. Now, the inverse will do the opposite. That's why it's called an inverse. It's going to take everything in R and bring you back to D. So practically then, the domain of the inverse is R, the range of f. And the range of the inverse is D, what used to be the domain of f. So the theorem, or this result, will tell us that if f is continuous in D, so if f is continuous in its domain, in other words, is continuous at every x in its domain, then the inverse is continuous in its own domain R. So I'm going to say then f inverse is continuous in R. And just as a little reminder, that R is the domain of the inverse. And I'm hoping that you're not finding this shocking. This is actually quite predictable. We're saying that if we have f and its inverse, and if we know that f is continuous, then f inverse has to be continuous in its domain. And why do I say that this is obvious? I mean, think about how f and its inverse are related. Let's see. Imagine that I have here the y-axis. I have the x-axis right here. So this is y and this is x. And let's say that this is the function f of x. What is the significance of an inverse? How do you build an inverse? Well, what you do, if you remember, you take the line y equals x. This is a little bit, okay, like this. Y equals x all the way down like this. And then you take the original function, you take f, and you reflect f about the line y equals x. So you just do a reflection. So practically when you do your reflection, you're going to end up getting something like this. The blue graph is going to be the graph of the inverse. So then a reflection, that means that if you started with a continuous function, continuous means that there are no holes, there are no jumps, there is no infinite discontinuity. If you start with a clean, beautiful connected graph, when you reflect, you don't ruin that beautiful connection. The reflection will continue being a beautiful, smooth graph with no jumps, no holes, and no infinite discontinuity, because you're only doing a reflection about a linear function. So in that sense, this result right here, it's pretty straightforward. So now you know every function and its inverse behave similarly. If f is continuous, its inverse is going to be continuous as well. So you can always make that assumption. I want you to look at this table right here. This one says that the following types of functions are continuous at every number in their domain. So this is now, all of these functions are going to go in our toolbox. We already said that polynomials are continuous everywhere. Rational functions, these are polynomials over a polynomials. We already said continuous everywhere except at the values of x that makes the denominator 0. Root functions, or what I was calling before rational power functions. These are functions that involve square roots, cube roots, or functions x to the p over q. All of these functions are continuous in their domains. Trigonometric functions. Oh my goodness, think of sine, think of cosine. These are all beautiful connected graphs. You can trace through the entire sinusoid without ever having to lift your pencil. The only one that we have to be careful about is tangent, because tangent has infinitely many vertical asymptotes. But if you pretty much only focus in the domain of tangent, right? Tangent has a vertical asymptote at negative pi over 2, and then it continues at 3 pi over 2. I am only going to do one cycle, however. Within the domain, within its own domain, tangent is beautifully continuous. So as long as you exclude all of the vertical asymptotes, tangent will be continuous in its domain. And we already know that if a function is continuous, its inverse will also be continuous in its domain. I mean, if you think about the inverse of tangent, right? The inverse of tangent. So tangent is invertible. If you remember from pre-calculus, tangent is invertible in the interval from negative pi over 2 and pi over 2. So if you just look at tangent within this interval, then tangent has an inverse. And the inverse of tangent is now going to be at, it's going to be bounded by two horizontal asymptotes at pi over 2 and negative pi over 2. The function itself is going to look like this. It goes up and up like that. So here is tangent of x. And here is tangent inverse of x. And you can notice, right? You can see that between negative pi over 2 and pi over 2, right here, tangent is beautifully continuous. And when you look at the inverse will also be continuous. Then exponential functions. Exponential functions are also beautiful, well-behaved. I call them well-behaved functions. There are no holes, there are no gaps, there are no asymptotes, nothing like that. So if exponential functions are continuous, logarithmic functions are going to be continuous as well. Because you must remember from pre-calculus that exponential functions and logarithmic functions are inverse of each other. Here is a typical exponential function right here. It increases from left to right. So this is, let's say, y equals b to the x. And then you already know that if we take this exponential function, this is the line y equals x, and we reflect the exponential function. So this is going to go here. If we do something like this, we actually get the inverse. Let me call this y to the negative 1 for the inverse. This is going to be the logarithmic function. So again, if we start with a continuous function, and this continuous function has an inverse, then the inverse is going to be continuous as well. So all of the functions that are listed in this box right here, we can now assume that are always continuous. We don't have to prove that. We don't have to convince anybody of that. Polynomials, rational functions, root functions, trig functions, exponential, logarithmic, the inverse trigonometric functions, those are all continuous functions in their domains. Let's look at example 2. Example 2 is asking where is the function f of x, which is made up of the sum of other functions like logarithmic functions. This is the natural logarithm or shortcut ln x. Remember, ln x is a logarithm with base e, and e is a real number approximated as 2.71. It's irrational, it keeps going on forever, but ln, natural logarithm, it's a logarithm with base e. Then we have the inverse trigonometric function for tangent, tangent inverse, and then we have a beautiful polynomial, a quadratic in the denominator. So where is this function continuous? What we're going to do is we're going to use all of the tools that we have so far. So we know that ln x is continuous. Let me start though noting where they are continuous. So let's start with ln x. I know that ln x is continuous. If you think of the graph, I need you to visualize the graph. I already drew it kind of on the last discussion. If you remember, ln x being a logarithmic function behaves like this. The y-axis is a vertical asymptote and is increasing from left to right. So ln x is continuous everywhere from 0 towards positive infinity. So what I am going to do is I am going to go to my line right here and I will just shade where this function is continuous from 0 to positive infinity. But I want to emphasize here that 0 is not included. I should have an open circle there. It's going to get a little bit messier. I mean my number line, so the open circle is going to somehow get lost, but all right, try to bear with me. Now let's go ahead with the second function that we see, tangent inverse. Tangent inverse of x, and we just did that in the previous discussion. Tangent inverse is continuous. Just quickly, I'm going to draw it here. If you remember, tangent inverse has a horizontal asymptote at pi over 2, and it has another horizontal asymptote at negative pi over 2. And the function looks like this, beautifully continuous. It is continuous everywhere within the entire real line. So continuous from negative infinity to positive infinity. So now if I shade, let me shade a little bit above here, I will shade the entire real line, and this is for tangent. Now continuing, we have the quadratic, x squared minus 1. So x squared minus 1 is continuous everywhere. So within all real numbers from negative infinity to positive infinity. If I go over here to my graph, again, I would have to, let me use a marker. I would have to shade the entire real line like this. Okay, so that's what we have. Now, these graphs or these functions are not in isolation, right? They are all combined through addition and division. When we have division now, we are going to have to be cautious of values of x that make the denominator 0. So there are two values that I have to go ahead and exclude. Just like we excluded 0, we have to exclude negative 1. I'm going to put a big circle. I'm excluding negative 1. And we are also excluding 1 from this list. Also, the domain of a function like this, whenever there are several functions combined, I have to choose values of x that make everybody happy. It's like being in a party. I mean, imagine how many people you can have in your birthday party. Well, if you're going to give cake, you have to give cake to everybody, not just to one person. You cannot leave one or two or three people out. Everybody has to get a piece of cake. Everybody has to be happy. Everybody has to feel satisfied. So something similar here. All of these functions kind of have different domains. But whenever I consider all of them together, they all have to be happy within the domain. F of x has its own domain. So the domain of f of x will consist of all the values of x that satisfy all three functions. Practically what you want is to look at this number line and to see where all of the three colors overlap. And if you notice, the three colors overlap right here up to 0. I see green and blue and red all through here. I know that we are excluding one, but then the three colors overlap again here up to 0, not including 0, because ln excludes 0. Then when I go to the left of 0, then that's not good anymore because I completely lost the red shade. I only have the shade of green and the shade of blue. So pretty much everything in here, it's already dead. I'm going to put an X right here. We're not going to even look at that. So practically then, we're going to look at the interval from 0 to 1, but not including 1, and then everything to the right of 1. That is going to be the domain of this function. And this is where this function is going to be beautifully continuous. So we will say that, therefore, f of x is continuous exactly in its domain. It's continuous in the interval from, let me go ahead and state the interval in interval notation. Sometimes students find that easier than set notation. So we're going to go from 0 to 1, not including 1, or remember union is called the union symbol. That means or, from 1 all the way to positive infinity. So this is the domain of the function. This is where f of x is continuous because this is where all three functions feel happy together. This is exactly where all of the three functions can operate in any x value. Because if I choose an x value, let's say that is here, imagine that I pick x equals -2, tangent will be happy with -2. So if I plug in a -2 here, I'm going to get a y value. Great. X squared minus 1, super happy with -2. If I plug in -2, I have a beautiful y value. But ln x will be extremely unhappy with -2 because the ln of -2, just like the log of any base of -2, is undefined. So these values over here are not okay for ln. That means that for the entire function f of x, those values must be excluded. With 1 and -1, ln is happy with 1 and -1, tangent inverse is happy with that, but then the denominator is going to be unhappy with that, so they need to be excluded. So practically that leaves us with everything between 0 and 1 or everything greater than 1. So there we have continuity. The last class of functions that we need to tackle here are composite functions. Composite functions occur everywhere. So we need to be able to know how to handle continuity on composite functions as well. So I got started here with the original statement of the next result. We are saying suppose that h is a function, but h is a composite function. It's a composition of f and g, two other functions. So this is h. We are going to pick x equals a, and the question will be here, when is h continuous at x equals a? So this is what we want to investigate. What is the condition for continuity of a composite function? And again, look at this. H is a composite function. G is the inner function. F is the outer function. H is a composite function. So if we pick a number a in the domain of H, we are trying to argue for continuity of H. How do we argue that H is continuous at A? How do we do that? So this is what this result will tell us. So that result begins like this. If the inner function, so if G is continuous at x equals a, and this is very important here, and f is defined at g of a. Very important. Remember, as a composite function, the inner function is the function that is going to act first on a value of x. G is acting on a. We want G to be continuous there. But to be continuous, that means that we're going to have G of a inside. We want f to be defined at G of a so that we can continue the composite process. So if G is continuous at A and f is happy with G of A, then the composite function h of x, then h of x is continuous at x equals a. Okay. Remember that we have a function h, and we're trying to argue for continuity at a. Continuity of h. H is the composite function. So h is continuous at a as long as g, the inner function, is continuous at a and f is happy with g of a. If everything goes nicely together, then h becomes continuous at a. With example 3, I want to show you how to use now the result that we just went through about composite functions. How do we do that? I want you to look at A, is a composite function, and even look at B, another composite function. So the problem is asking us, where are the following functions continuous? On which intervals are they continuous? On which values of x in some interval? So why don't we start breaking the function apart? Let's start from the inside out. The inner function here happens to be x squared. So we know that x squared is continuous. We already know as a polynomial or as a power function, x squared is continuous, and you never have to convince me of that again. X squared is continuous in its entire domain, all of the real numbers. And we know that sine of x, just as a function itself, sine is continuous also in all of the real numbers. So what this is saying is that no matter what x squared dumps in here, sine is going to be okay with whatever x squared puts in here. Sine is okay with anything. So that means that if everything goes beautifully together, x squared is continuous everywhere, and sine is going to be happy with whatever x squared puts in there. Therefore, we know that sine of x squared, which is h of x is going to be continuous also in negative infinity to positive infinity. So that's how easy you can argue continuity of composite functions. Now, I want to give you something that is a little bit more challenging, right? What's the point of just doing easy things? Let's do something that has a spice in it. So let's look at B right here. F of x is equal to ln, the natural logarithm of 1 plus cosine of x. Remember, ln is a logarithm. So 1 plus cosine x. Let's think about what kind of values 1 plus cosine x is going to put inside of the logarithm. With logarithmic functions, we have to be a little bit more cautious. Logarithmic functions, they do not like everything. You know that a logarithmic function, the domain of a logarithmic function, is consists of just 0 to positive infinity. And this is where logarithmic functions are continuous. They are continuous only within 0 and positive infinity. They don't like 0. They don't like anything that is negative. So whereas 1 plus cosine of x, 1 plus cosine of x is happy with anything. They are defined within all the real numbers. So let's be careful here. Let's explore 1 plus cosine of x a little bit further. What do we know about cosine? We know that the cosine of x happens to be between -1 and 1, right? The simple cosine graph. Think of the cosine graph. Let's say now, though, that I add 1 to every part of the inequality. So I'm going to go ahead and add 1 over here. So plus 1, and plus 1. Whatever I do to one side, I do to the other two sides. If that's the case, I am going to have 1 minus 1, 0, less or equal 1 plus cosine, because I'm adding 1 to the middle as well, less or equal than 2. This is telling me that 1 plus cosine of x will be between 0 and 2. So pretty much everything that's going to go in here is going to be between 0 and 2. But 0, that's a little bit dangerous. Ln is not going to be happy with 0. And the thing is that 0 will happen at infinitely many x values. I would like for you now to visualize the graph of 1 plus cosine. If you notice, here it is. I have it all drawn. It's all drawn out here for you. So this is the graph. This is the graph of y equals 1 plus cosine of x. And as we found out, the range of this function inside 1 plus cosine is going to be between 0 and 2. You can see it right there. Remember, this is a composite function. Inside, we have 1 plus cosine. Outside, we have the natural logarithm. So 1 plus cosine takes on any x value and is going to put values of y between 0 and 2 into the logarithm. The only issue with that, this is the issue here, that 1 plus cosine is going to be 0 here, and then later on here, and here, and here, and infinitely many x values. These x values happen at pi over 2, and then every 2 pi n. So every other cycle, every period. So we have to find a way pretty much to exclude those x values. In other words, the composite function, so ln of 1 plus cosine of x, is going to be continuous, but continuous except at the values where the inner function 1 plus cosine is equal to 0. Because, for example, if we choose pi over 2, 1 plus cosine of pi over 2 is going to be 0. You can see it right here on the x-axis. And then when you take, for example, the ln of 0, ln is going to be unhappy with that. It is going to be undefined. So as long as we omit or exclude these x values, I'm putting tiny x's, as long as we move those, we exclude those x values, then the composite function will be beautifully continuous. Ln has no issues with 1, with 1.5, 1.7, with 2. The only issue that ln has is with 0. And this is what is going to go inside of the logarithm. Numbers between 0 and 2, including 0. And 0 happens at infinitely many x values. So we have to exclude those x values. So then we will say that ln of 1 plus cosine of x is continuous for all x except x values that are equal to pi over 2 plus 2 pi n. Remember here that this n is an integer. N is an integer, just as you did last year in pre-calculus. So in set notation, this is a set where it is better to state it in set notation because you are now excluding infinitely many x values. So you cannot say, oh yeah, continuous in this interval, continuous here, or here, or here. So interval notation becomes very inefficient. So let's use set notation. So we have continuity, right? Continuous. So in other words, h is continuous for all x values such that x does not equal to pi over 2 plus 2 pi n, where x can be any other real number. So this is exactly the place where the function is continuous. At every x, except when 1 plus cosine is equal to 0. And 1 plus cosine, let's go back to the graph, is equal to 0 at pi over 2 and then every 2 pi n. So we have to exclude those x values. And again, this is a case that it is better to use set notation. If we want to use interval notation, that will be impossible because we have infinitely many intervals that we would have to state, and that's impossible. So these are two beautiful functions. One composite function that is straightforward to argue for continuity, and then another one that has a bit of a spice where you have to think a little bit more carefully about 1 plus cosine and what kind of values 1 plus cosine is going to dump inside so that the logarithm can be happy with that. We have to think about that a bit more carefully.